We're ready to restart. So the next topic is the network layer that we have seen is using packet switching. The most spectacular part of the network layer is, of course, the IP addresses. So what are those things? Here is an example, a snapshot of the EPFL network, or a fraction of it at a certain point in the past. And you see that there are numbers everywhere that are called the IP addresses. When you read things on the internet in blogs and forums and documentation, sometimes just people say the IPs. IP stands for Internet Protocol. We'll see why it is called in this way. And the correct term is IP address, but many people say IPs. An IP address is a number that is allocated to a physical interface. For example, my laptop here uses Wi-Fi, so there's an IP address associated to this Wi-Fi interface. When I go to my office, I connect it to Ethernet. I have another IP address. So different interfaces have different addresses. Other than that, they are just numbers. IP exists in two versions. The old version, which is still the most widespread use, and at EPFL, unfortunately, sometimes we have only this one. It's called IP version 4. Versions 1, 2, 3 were experimental versions that very quickly evolved towards version 4, which is the first large-scale mature version of IP. And IP version 4 addresses are 32 bits. Because it was invented in the 70s, at that time, people did not use hexadecimal digits. So when you write a string of 32 bits, you don't write bits because it's completely unreadable. Today, you would write it by using hexadecimal digits, right? You would use 8 hexadecimal digits because an hexadecimal digit corresponds exactly to 4 bits. But this is not the way it was done. It was done using decimal representation. 4 decimal numbers that each represent 8 bits. So a decimal number that represents 8 bits is between 0 and 255. So you have 4 numbers between 0 and 255 that each corresponds to 8 bits here. When using that, so we will constantly need those numbers, it's useful to remember that a string of all ones corresponds to the decimal 255. And if you look at those IP addresses of EPFL, for example, the MAC on the right has the address 128.178.29.64. The PCs on the left have similar but slightly different addresses. We see that I said IP addresses are just numbers, but like telephone numbers, they are structured. Just like telephone numbers, at least in the old days, if you had a 021, you know it was in the Lausanne area. It's similar here. If you have an IP address that starts by 128.178 or 128.179, so the first 15 bits corresponding to those two numbers, that is allocated to EPFL. Blocks of IP addresses are allocated to entities. Who are those entities? Today, they are the internet service providers, Swisscom, Sunrise, AT&T, etc. The internet service providers are the entities that need IP addresses. So the entity that manages the numbers ICANN and related incarnations of it allocate blocks of IP address to regional organizations. Regional for the ITF means Europe, for example, is one region. So Europe receives one block of address, which then gives it to different operators in different countries. And long, long ago, also big enterprises or campus like EPFL could also receive their block. So EPFL received a block because it was at a time where Swisscom probably was not even providing an IP service. Question?
Are ISPs always linked to mobile network services also, or is it just a business consequence that Sunrise and Swisscom, they all are services provider and mobile network provider?
So are internet service providers also mobile network providers? Practically, yes. I mean, most of the internet today is mobile. So they're still wired for watching Netflix, but for the rest, it's mobile. So of course, in theory, no. In theory, you could be an ISP that provides only a wired service. I'm not sure you would make a lot of business, but it's from the IP address viewpoint, it's completely orthogonal. Right? So this was allocated using allocation mechanisms that are political allocation mechanisms that today are governed by entities that are derived from the IETF, and also by political entities that give them to the associations of internet service providers. So if you want to run an internet service provider, you will need to become part of such an association and then obtain a block of IP addresses. What we see here is that IP addresses are structured in the sense that the first part of the address, the prefix here, is a reminiscent of the block. So you can analyze by having an IP address whether this was allocated to Swisscom or Sunrise. And this is how you can infer in which country you are. This is how Netflix decides that if you have a French subscription, you cannot watch that movie from Switzerland, for example. Of course, in practice, you can go around that with VPNs and things that we will see later. So the old numbering plan is IPv4, uses 32 bits. Now, if you think about it, with 32 bits, you can address how many different interfaces in the world? 4 billions, exactly. 2 to the power 32. If you take the log 2 is 0.3, so that the decimal log is 32 times 0.3. That gives a total of 4 billions, right? 4 to 10 to the power 9, which is less than the size of mankind. So, and since each of us has more than one IP address, it's not enough for everyone. In theory. In practice, it is enough, and we will see by which mechanisms, because addresses can be reused, and there's lots of private addresses. However, this is still at the limit of feasibility. Therefore, a new numbering plan was devised, in fact, in the 90s, 97, if I remember well, so more than 20 years ago, which expanded dramatically to 128 bits. So by making it 128 bit, we put it to the power 4, this number, and then it becomes a truly astronomical number. Some people say it's the number of atoms in the universe. So that's about this number. So you can truly allocate one IP address to everything. So people believe with this new numbering plan, there are enough IP addresses, so it's probably the last one that mankind will invent. Yes?
So IPv6 was introduced because of the postgraduate IP. Do you know by any chance how much percent of the IPv4 is currently?
So right now, the IPv4 space is totally used. Completely. So you cannot, if you start your ISP business, you will not have IPv4 addresses. They will give you new addresses that will be IPv6. However, there's lots of blocks that have been allocated. For example, EPFL has a block with 15 bits of prefix. That means we have a huge number of addresses, right? We have 2 to the power 17 possible addresses at EPFL, which is first much more than we need. And second, as we will see, most addresses that we have at EPFL are private addresses, so that they're not even in that space here. We'll see there's a trick to use another type of addresses, but we'll come back to that in one week here. The motivation, the why of this was to increase the size of the address space. And that's a problem for ISPs today, but, and we'll come back to it, it has a lot of side effects. Because of that, there is a new numbering plan, which is uses much larger addresses, so 128, or the Google name servers like 8.8.8.8. They are very nice in IPv4. In IPv6, here are 2 examples of IPv6 addresses. You see they are very, very long, because that's 128 bits. We write them as sequences of hexadecimal digits, right? And typically in lowercase. So for example, 2001, which is read 2001, although it's not the number 2001, it's the hexadecimal number, that is 200. It's much larger than 2001, but people read it 2001. That's the block that was standardized in the year 2001, and that's the one that is used for public IPv6 addresses today. So an EPFL public address could be this one. And there are also what are called private addresses, like with IPv4. Private addresses are addresses that can be used only inside a certain scope, typically, for example, inside EPFL. In IPv4, those are 10 dot something addresses, for example. There are other ones that we'll discuss. That means if I send a packet from here to a server in California or to Google or whatever, this address will not work. because I'm exiting the private domain. So we will need some form of mechanism to translate those addresses into public addresses that are called network address translation boxes that we will discuss a bit later. Second piece of information, unfortunately, IPv4 and IPv6 are incompatible. So if you try to call a server by using IPv6 and this server works only on IPv4, it will not work. So this because an IPv6 packet is not an extension of an IPv4 packet, it's a different type of packet. Some of you may be exposed to very weird and old things, like if you work in industrial networking environment, you will have protocols that are not IP, that uses protocol developed by Siemens, for example, for communicating between safety installation and railway system. They use non-IP protocols. If you try to talk to such a machine using IP, of course, it will not work. You're using incompatible protocol. So IPv4 and IPv6 are the same with respect to each other. They are two incompatible protocols. An IPv4 packet sent to an IPv6 machine is not understood. Question? Yes, and for that, I invite you to look at the archives of the mailing lists of IETF, of the IPv6 group of the 90s. You will see all the long and year-long discussions whether we should be compatible or not. There are pros and cons of being compatible or not. Of course, being compatible makes the transition much easier. We will see that there's a certain difficulty in the transition, which, by the way, is good for us because we're studying TCP-IP, so it gives us some interesting business to do to interoperate some otherwise non-interoperable things. But there are also many drawbacks, and the drawback is called the IBM syndrome. The IBM syndrome is IBM has traditionally, not anymore, but in the past, was very proud of saying, we continue to maintain everything. So when you were working at IBM, like me in the 90s, you had to be compatible with all the things that had been developed since the 60s. So you had, and since technology evolves so quickly, that quickly becomes completely ridiculous at some point. So it still doesn't work to be backwards compatible all the time. Those of you that are working in open software development, that's also one of the recurrent questions that come. When you fork a certain development, do you want to be backwards compatible or not? If yes, then that's good. That makes the transition easy. But over the time, that becomes a pain because you need to continue to support things that are less and less used to the point that they're not used at all, except by one device somewhere, a printer or something in an elevator. You still need to be able to connect to that. So that's the issue, compatibility versus incompatibility. I mean, Apple is very good at not being compatible. Right? They do a new, the M1, the new POF, the virtual box, all that stuff doesn't work anymore. It makes them also more agile, better software. Things that are always compatible come with a complexity. I personally think it would have been a better idea because we're just talking of the format of an address, not all the zillions of aspects of software. I personally think, I was of the opinion it would be better to be compatible, but obviously I was not mainstream. So this is not what has happened. Question?
Are the reasons why we are not doing that much IPv6 political or technical?
Why are we not using very much IPv6? Well, first, it depends. It depends whether you're using it or not. For example, I had the surprise I think 1 year ago when we were forced to work at home. I bought a new printer and everything, and it didn't work. Tried very hard everywhere, it didn't work. Why didn't work? Because I just moved my computer from my office to home, and my printer worked only with IPv6, the new printer I had bought. Right? So the default configuration, everything, the plug-and-play configuration with IPv6. And I had disabled IPv6 because here at EPFM in my office, if I use both IPv6 and IPv4, some services have poor performance. So we should be careful when saying where it depends. It's true that at EPFL we're exposed to more IPv4 than IPv6. I think home networks, if you buy modern equipment, by default, the plug-and-play configuration will be IPv6. Devices, Zigbee, sensors, everything will also tend to use IPv6. Swisscom and Sunrise will also give you an IPv6 address by default with your equipment. But it is true that many developments are still done with IPv4, which is a pain. I mean, if you start something new today, we should do it with IPv6, because sooner or later, you will be confronted with the need to make it interoperable with IPv6. So it's better to start now. Now, the good news is that this is all software, right? So our software changes every week in principle. If you want, for security reasons, or your cryptography software needs to be updated probably very, very frequently. So changing from IPv4 to IPv6 is only software. It's not hardware. Thanks to the MAC layer, as we'll see, the MAC layer, which is implemented in hardware, is practically entirely independent of IPv4 versus IPv6. But still, there are problems and issues like last time I checked the IPFL library to check whether you are allowed to access some resources. We'll see whether you're at IPFL. How does they know if you're at IPFL? By looking at your IPv4 address. So if you access it with IPv6, they're unable yet to recognize that this is an EPFL address. It's just a soft, because the people who did it probably didn't care about IPv6. Of course, if we switch off IPv4 at EPFL, people will detect the problem and it will be quickly changed. That's for addresses. Most of the time, we don't see addresses. In fact, it's only in this course or when you are developing software that you're exposed to addresses. In principle, we see names. Names were invented because people thought that addresses are not human-friendly. So it's sending a packet to 128.179.156.15 is doable. With IPv6, it becomes less doable. So instead, you think of an interface by a name. So names, originally, it's much wider than this, but you can think as a very first approximation, a name is a name of an interface. So it's a synonym for an IP address. Except the link between the IP address and the name is completely arbitrary and is done by a directory called the DNS. So there is no physical reason. So for example, in particular, the name may change when I am at EPFL with this laptop here. This address may be associated with a name, but would be different if I move somewhere else. And by the way, same thing for the IP address. Names are structured. They are, for example, ssc.epfl.ch, and as you know, the left is the most specific, the right part is the most general, the opposite of IP addresses here. And the two-letter at the end means it's a country code. So .ch is Switzerland, .li is Liechtenstein, .fr is France, etc. Three letters are the traditional top-level domains as they were done originally. So there's .com, which is the most known as for anything commercial, .net, that is for anything that has to do with the internet itself, .org, that has to do with organizations like United Nations, World Health Organization, etc. And then recently, anything became possible because the people who run the allocation of names realized that they can do a lot of money by selling names. So if you're a company called UBS, for example, or IBM, you can buy the UBS for probably a fraction of a million fee every year. And any name is possible. For example, there was an attack a few years ago. Somebody bought the name Sucks and created websites called Apple Sucks, and they blackmailed Apple to get money from them. If yes, there's a question on Zoom. If I have a laptop and a phone, they both share an IPv6 and use a NAT. Well, we will see that if you have both a laptop and a phone, and you're at home, for example, both of them will have a different IP address. And they probably are behind a NAT, and we'll talk about the NAT in a few hours. But I don't want to get into those details now. Now I want to put in place a few important things. The very first thing to realize is that names are not in packets. For example, when I go to a web server, I type somewhere, how do I know the address of the web server? Well, I had it recursively from another page that instructed me to go there, or I read it in the street, go to ssc.epfl.ch because you can study cool stuff there. So I go ssc.epfl.ch. In order to get to that server, my machine needs to get the IP address of that server. So it will go not to the final server, but to what is called a DNS. DNS stands Domain Name System. It will go to one of many, many servers that exist in the world that contain databases with this mapping, names to addresses. Who has such servers? Where ISPs. If whoever gives you a network service should also give you a DNS service. So if you're a customer, when you're at EPFL, you use the DNS server of EPFL. When you're at home with Swisscom, you will use, in principle, the DNS servers of Swisscom. There are also companies like Google who are happy to give for free their DNS server to the entire world. Those are the famous 444, 888, etc. DNS servers that are used when you live in a country where the DNS servers of this country, for example, are controlled and manipulated so that you cannot access some sites. But this is quite exceptional. Most of the time, companies are not happy to devote resources to maintaining DNS servers that cost a lot of money for people who are not their customers. Now you can say we are all customers of Google. This is why Google does it for everyone. So in this case, my machine will go to the DNS server of EPFL. How does my machine know what is the IP address of the DNS server of EPFL? Well, this is the configuration of your IP configuration must contain a valid DNS server address. Otherwise, your system will not work. We'll talk about IP configuration in a few more hours. So that's part of the configuration. It's not plug and play. IP is not plug and play. You must configure things. You may use configuration server or you do it manually, but it must be known out of band. You cannot use the DNS to know the name of your DNS server. You need somehow to bootstrap this information. So this machine at EPFL knows, for example, 128.178.15.8 as the standard name of the EPFL DNS server. So we'll send a request saying in one UDP packet, and if everything works fine, we'll receive a reply. The reply will be sent to, so in green is the destination address, which is the destination address of this user here, which will send to the port that we have seen before, the temporary port that has been allocated to this transaction by the operating system of the machine. And the text will be text of the type SSC EPFL is this. The format of this text is precisely the DNS protocol. This is what DNS specifies, how we encode this message. After this is done, my machine knows the IP address of the server, and I can go there and ask, for example, to get some object that will be returned to me here. So when my transaction to the DNS server occurs, at least in the IP packet header, there is not the name of the server that I'm sending it to. It is probably in the text one, because the HTTP protocol usually asks that we identify the object by putting the name of the server or the location, followed by the local name inside this place. Question? So the question is, the DNS server here is provided, for example, by EPFL, because this user is at EPFL. How does this machine know? Well, when you first join the EPFL network, there is a configuration phase, which is probably for you using so-called DHCP. So by default, your machine uses DHCP. So that's an automatic configuration. It will talk to a configuration server. When you first enter the first Wi-Fi station of EPFL, your machine will talk and will get its IP address and also the IP address of the DNS server of EPFL. And as I said, when the packet is sent from the user on the left to the web server, the packet will be something like this one here. You will see a destination address, which is an IP address, followed by a message. Inside the message, there may be the DNS name of the resource, but this is not used for the packet to find its way through the internet and through the routers. Routers look only at IP addresses. They, in principle, if they are not trying to spy on you, they, in principle, do not look at the content, because most of the content on the internet is encrypted, so IP routers cannot really understand what's inside IP packets here. So that's the IP layer, which will, at least a first glimpse of the IP layer, will discuss more aspects of it and all those things of auto configuration and everything, how this is done in detail, and how things can be bad if they don't work. This will be the topic of the coming lectures and labs. Now, if we continue the layers below, when I say layer below, we have a layer called IP and a layer called transport layer. The interface between the two is how the transport layer, how the socket subsystem in an operating system uses the IP packets here. It's not an interface that you can usually access easily as a programmer. If you're not working in the Linux kernel, or if you're not working at Microsoft in Windows development, you are not able to access this interface here. But there is a well-defined interface, and here I'm showing the box in green and orange to make the difference between the, in the green world, there is a separation between what we call the network layer and the MAC layer. Those two things are in fact the network. But you should not repeat what I just said, because every paper, every literature will say, no, the network layer is what we just saw with IP addresses and routers. But in fact, you can also connect devices without routers. In fact, you can connect, you can go to Migros and buy what is called a multi-port a bridge, which looks like simply an extension. If you have several Ethernet cables, you can connect several together, and you can have several machines together that are interconnected without a router. And in theory, it could work even without IP addresses. And originally, this is how it emerged. Because, why did it emerge in this way? Well, because when this was developed in the 70s, TCP-IP was completely obscure. There were perhaps a few hundred people in the world who knew about TCP-IP. The rest was using marvelous things like AppleTalk, novel netware. So there were computer networking things, or perhaps the most famous one was DECnet, that worked with given machines. If you had Mac machines, they would communicate with each other and with the printer using AppleTalk, which was not using IP at all. There was no IP address, not anything. If you were using Windows, then good luck. It was more clumsy to manage to send something to the printer. It was using novel netware, or there were multiple different protocols not integrated in Windows, so you had to add it, but still it worked. And the most modern and fancy thing was DECnet for the digital machines that used also its own networking system. That one was very close to TCP/IP. And then in a corner, in a few universities, there were a few freaks who were playing with things that were called TCP/IP that later replaced everything. But because this is how the world was, to interconnect systems, you did not want to use one specific network layer, which is what Apple did. You had networking devices of Apple that worked with only Apple devices here. But there was a need to do it in a way that is more independent. And that is exactly the MAC layer. Now, the way we can, so it exists because of the evolution. It evolved before, in fact, the Mac existed, before IP was anything important. So the MAC layer exists today, roughly speaking, in two versions. On the right, I'm showing an Ethernet switch, one of the boxes you can buy for 30 francs at Migros that has multiple Ethernet sockets, and you can connect devices with Ethernet cables into it. And all together, they already constitute a network, which means I can send a packet from one machine to another and it finds its way. But the most popular way today is Wi-Fi. The Wi-Fi LAN does the same, but it replaces the cable by wireless channels and a base station. But mentally speaking, it's exactly the same thing here. Such a system does not use at all IP addresses. So when, for example, computer A over such a system sends a packet to a computer for example, to a smartphone in the middle, or to another machine that could be a router, for example. It is not used. So IP uses IP addresses to know whom this packet should be sent to, like the zip code in the post office. Here, the MAC layer does something similar, but with its own addresses that are called MAC addresses. So MAC addresses are not IP addresses at all. They are just numbers, 48 bits. And here's an example of a MAC address. They are structured into half of the address is allocated to the manufacturer because the MAC layer, mentally speaking, is hardware. So for many people, MAC equals hardware, IP equals software. This is an oversimplification. It's not true, but this explains why things are the way they are. It's not true because the first MAC layer, the first bridges, for example, were pure software systems. And today you have IP routers are a lot in hardware, and there are even integrated circuits that do TCP and IP in hardware. So as I mentioned already, the implementation in a given form is something shaky that changes over time, that depends on your environment, and should not, you should make the difference between architecture, a concept like the IP layer, and a given implementation. Is it a box? Is it a hardware system? Is it just a piece of code in my computer? But mentally speaking, this was how it was. A MAC address is therefore, I mentioned that my computer has two IP addresses, one for Wi-Fi, one for Ethernet. Well, it has also two MAC addresses, one for Wi-Fi and one for Ethernet. The difference is that the MAC addresses are given by the manufacturers of the hardware. So my Wi-Fi card is manufactured, I don't know by whom, but by one company. The company that manufactures the Wi-Fi part of my computer, card or chip, allocates a MAC address to this interface by typically receiving a block of MAC addresses from the IEEE. It's not the IETF that does it, it's IEEE. IEEE is the professional organization of all electrical engineers, but well beyond electrical engineers, also computer science, communication systems. If you're not yet a member of IEEE, you should. So I invite you to apply, and I'll be happy to fill in the forms if you want. That's, I think, something that for your profession might be very useful. End of the parenthesis. So IEEE, which is typically more oriented towards hardware standardization, IEEE takes care of standardizing the MAC layer, therefore allocates also the MAC address here. How does it work? When computer A sends a packet to a machine B, well, as usual, you need to put as destination address the address of this thing. This is how Wi-Fi works. When I send a packet to the base station, the base station looks at the destination MAC address and will know, hopefully, to whom it has to send it to. If it doesn't know, it will broadcast to everyone. So the MAC layer typically may use some broadcast. Now, with such a system, of course, you're very limited. I'm showing here my left system, Wi-Fi, and my right system, Ethernet. You can work with that without a router, but routers were precisely invented to interconnect such systems. Such systems are called local area networks. So a local area network, if we stick to the English meaning, it means a network that's local. But in the concept of computer networks, it means something much more specific. A local area network means a set of devices that are able to communicate at the MAC layer by just knowing the MAC addresses of each other. So all the things on the right constitute one local area network, LAN B. Because if the MAC on the top sends a packet to the printer, the only thing that each needs to know is their MAC addresses. Question? Is there an equivalent of DNS for MAC layer? No, there is no DNS for MAC layer. We never heard of that. We will see there is another mechanism, which is called ARP, Address Resolution Protocol. Of course, the same question arises with MAC layer. How do I know that what is your MAC address if I want to send a packet to you? That will be the topic of Address Resolution Protocol. How do I know your IP address? Well, I go to DNS. If you're a server and I want to find your IP address, given your MAC address, how do I know it? Most of the time, I don't need to know your MAC address. Because if MAC address is used only to communicate within a local layer network. In some sense, I'm using circular definition. A local area network is a set of devices that can communicate using only their MAC addresses. But the consequence of this definition is two things. First, in order to interconnect them, you don't need routers. You don't even need IP addresses, even though in practice, everybody today uses IP to communicate, even if you're in the MAC in a LAN, but you must not. Question? So if I understand well your question, is it possible to send a packet from one device to another using only MAC addresses? The answer is yes, but that's clumsy. Again, because it's done in the hardware. So this is done by what I mentioned, some of these old style devices. If you use a field bus to communicate from an actuator to a sensor, they may well do that. And there are protocols who do that. If you work with some companies that work in industrial automation, Siemens, for example, they have devices that do that. So when they communicate from a railway safety mechanism, they don't, part of the system don't use IP addresses at all. So they have big tables that say the railway equipment, blah, 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 has this MAC address, and they use that. They're all moving to IP because IP comes for free. And now there is some considerable work doing that, but that exists and is possible. It tends to be obsolete, but exists. Yes?
I can't have more than 48.
Correct. So the 48 bits, well, first, it's still a large number, right? It's a 2 to the power 48. So it is a, I don't know, but millions of billions. So it is still a very large number. And this number is being extended to 64. So some equipment start having 64-bit MAC addresses. So, and 64 bits is probably large enough. Nonetheless, if you have a local area network, which is typically local in the sense you will not have many, many devices. The largest local area networks I've seen in my life had 30,000 devices, and that was an exceptionally large local area network. Today, most local area networks have at most a few hundred devices. Because it doesn't scale. We will see why it doesn't scale, but it's easy to understand already now. The MAC addresses are hardware addresses. If you have a bicycle, probably on the frame of the bicycle, there's a number put on it. Well, think of the MAC address exactly like this. It's the serial number of your communication adapter. So imagine you use MAC addresses in the internet. Imagine you are a router in the backbone of the internet, and there is 1 billion different devices that you need to interconnect. Well, you need a table with 1 billion entries, and there is no structure. It's a complete mess because your serial number of your adapter has nothing to do with yours, even though you both are in the same auditorium here. So your packets, now if we look at IP addresses, we know from the structure this has to go to EPFL. So the backbone routers of the internet don't need to know specifically where you are now. They just need to know, how do I go to EPFL, which is 128, 178. So I don't need to know all the addresses. That is called address aggregation. The IP layer can aggregate addresses because the address is structured. With IPv4, there is some structure. With IPv6, there's even more, which means that if you're far away from somewhere, you don't need to know all the details of that somewhere. You just need to go the beginning, the prefix. MAC addresses don't have that feature. They're just serial numbers. This is why it is not scalable. This is why it is maintained. It is used only in local area networks. The question one might ask is why we have that. Why we don't simply use IP addresses everywhere. And there are, once in a while, there are proposals to do that. But now there's a good reason for still having MAC layer. It is that if I use IPv6 and IPv4, for example, the devices here, the switch and the Wi-Fi base stations are not affected, at least for their basic function. They might be affected somehow because if it's an intelligent switch that I can remotely access to manage it, there is a web server in it. And this web server probably has to respond to an IPv6 address. But for the basic layer, this is not affected by the time. It is not impossible that in the remote future, MAC addresses are replaced by some form of IPv6 addresses. in which case the boundary between the two would blur. But right now it does not. So right now we have to learn, and probably for the coming 10 years, there will be a difference between MAC layer and IP layer. Because of this structure, we have something that is visible also at the IP layer. In fact, if we do the etymology of IP, IP stands for internet. It's not net. We call it the internet. Where does this inter comes from? It comes from this. The internet, IP, the IP protocol, was developed as a mechanism to interconnect local area networks. When our network became too large, we put a router between different local area networks, like I did in the previous figure. This is why it is called the internet. Right? The net, in that case, is the LAN, and the internet is the IP. Now, of course, this is a bit obsolete. We think of the internet as the network, but originally this is where it came from. This becomes visible in a part of the configuration. We saw that an IP system must be configured, obviously, with its own IP address, also with the IP address of the DNS server. It must be configured also with something else, which is called the network mask. The network mask is something that says which of the bits of the IP address identify the local area network that I am in. The terminology is different depending on whether you're sitting in the MAC layer or you move one level and you go to the IP layer. Seen from the IP layer, a local area network is called a subnet. So subnet equals local area network. Inside a subnet, all the devices can communicate without a router.